Across the United States Space Force, vital tactical intelligence is generated by the millisecond. But when siloed mission systems attempt to share that data, these streams slam into a bottleneck, generating an OODA loop lag that critically delays operational decisions. The conventional impulse for solving this silo problem is to build a massive, centralized repository. Software architects attempt to pull every piece of tactical data out of its native environment and dump it into a single data lake. In tactical defense, that approach collapses under its own weight. It forces invasive overhauls of legacy systems, strips data of its original context, and creates an enormous single point of failure for adversaries to target. For the Defense Innovation Unit's Project Hydra, Tensor Networks proposes a completely different methodology, the Hydra Tensor Fabric. Closing the OODA loop and achieving resilient command and control requires a system that can orchestrate data at sub-second speeds, without ever moving or consolidating the underlying legacy data. This outlines the four-layer Hydra Tensor Fabric, sitting alongside existing USSF networks. On the bottom left, the objective is end-to-end geodesic determinism, ensuring sub-second tactical C2 over legacy transport. The engine driving this is in the third column, the PTCP and TNQG runtime. To understand exactly how this engine achieves multi-enclave C2 at sub-second speeds, we have to build the system from first principles, starting exactly where the data originates. The foundational layer of the USSF consists of highly isolated tactical C2 applications, raw space and ground sensor feeds, and legacy databases. The first absolute rule of the Hydra architecture is source residency. Intelligence remains securely locked within the specific systems that generated it. Instead of extracting the data, the fabric integrates with these legacy systems non-invasively. It deploys lightweight sidecars, data adapters, and API facades directly at the edge. These adapters operate locally. They discover, normalize, and tag live event streams right at the source, adding structure without requiring a single alteration to the underlying legacy transport. Once the data is structured, a semantic layer uses Model Context Protocol, or MCP, servers to expose these unified streams. This creates a standardized language that allows automated agents and machine-to-machine systems to instantly query the data. This federated mesh renders live tactical data universally discoverable across the force, completely bypassing the massive security vulnerabilities and engineering delays of a centralized migration. With the data exposed, it must be routed to the end user. This is handled by the Predictive Tensor Control Plane, or PTCP, which enforces deterministic routing across the mesh. Standard routing protocols fail at tactical scale because they broadcast excessive telemetry. Every node constantly shouting its status generates massive overhead that ultimately chokes the network it's trying to maintain. The PTCP utilizes pole-TT modeling to compress this high-dimensional telemetry. By bounding the amount of data required to model normal fabric behavior, it severely limits overhead, even as the volume of mission data scales up. Instead of relying on rigid, standard routing paths, the PTCP uses conditional value at risk, or CVAR, geodesic scoring. It evaluates the dynamic geometry of the network, calculating the optimal compute path that actively curves around high-risk or contested node clusters. Continuously calculating these CVAR geodesics guarantees that event processing remains under 1 second, maintaining a resilient mission flow even when segments of the network are heavily degraded. Running concurrently is the Tensor Network quantum gravity layer. This mathematical model treats the entire network as a physical structure susceptible to gravity and tension. TNQG maps the mission fabric in real time. It reconstructs cut paths and visualizes geometric stress, allowing human operators and automated agents to see exactly where the fabric of the network is stretching or tearing. Traditional cybersecurity relies heavily on semantic security, scanning the actual payloads of moving data to look for known malware signatures. Hydra introduces payload-blind topological security through dTopo anomaly scoring. It doesn't need to read the data to know there's a threat. dTopo instantly flags and quarantines compromised sectors based entirely on anomalous geometric routing behavior. It detects the structural defect in the network's topology before a semantic signature is ever identified by traditional antivirus tools. Treating the network as a dynamic geometry provides an inherent zero-trust architecture, securing data across multiple complex enclaves without relying on payload inspection. Returning to the architectural block diagram, we see how the PTCP and TNQG runtime connects to the human operator at the Guardian mission layer on the far right. The direct output of this tensor native fabric is a real-time, unified, common tactical picture, a single pane of glass fusing live space and ground intelligence. This high-fidelity view gives operators the precise context required to execute AI-informed, operator-on-the-loop autonomous plans and rapidly deconflict units of action. Topological intelligence and complex geodesic math only matter because they culminate in a seamless dashboard, empowering the Guardian to act instantly with complete confidence in their data. Tensor Networks has structured an 18-month prototype timeline to move this architecture from concept into active field operations. At 6 months, the objective is rapid onboarding. Tensor will deploy a secret-ready evaluation enclave, connect the first tactical C2 interfaces, and establish observability metrics for data quality. At 12 months, the project reaches its MVP stage. The fabric will demonstrate collaborative mission execution across 2 distinct mission deltas using live data, proving the sub-second processing target in a real-world scenario. By month 18, the fabric expands to a 3rd delta. This final phase establishes cross-enclave release workflows, proving the system can maintain disconnected continuity and secure operations across strict security boundaries. This phased rollout guarantees minimal disruption to active operations, while systematically generating the rigorous risk management framework evidence required for full production transition. The Hydra Tensor Fabric actively rejects the latency and extreme vulnerabilities inherent in centralized tactical data lakes. By keeping data secure at its source and utilizing PTCP telemetry compression and CVAR geodesics, it orchestrates deterministic data access without moving the underlying files. Paired with TNQG and D-topo anomaly scoring, the fabric ensures mathematical security across highly complex, disconnected enclaves. Reconstructing and mapping the physical geometry of the network itself is what guarantees Guardians an absolute sub-second decision advantage from any authorized node.